Hey there!
Hey.
Section 3, Polynomials of Higher Degree and Modeling. This is where the fun begins.
Yes, because before now we've been talking about, in the first section, polynomials of first and second degree, linear, quadratic. Then we talked about power functions, and that got kind of crazy. Now we're back to polynomials, but higher than second degree, so third, fourth, fifth, sixth, and all that. We have some names for those functions.
We do have some names for those, and
Yeah.
sometimes you can use those names, but then it just gets to a point where you refer to it by degree.
Yes.
So
like the third degree is
cubic,
the fourth degree is
quartic,
and the fifth degree,
quintic,
sixth degree. Let's
degree
not go there.
6.
Yeah.
I just call it, if you've got a sixth degree polynomial that we're graphing, it's a sixth degree polynomial instead of hexagononial or whatever. What would it be?
I don't want to say.
Okay.
Okay.
Fair enough.
Okay, it's a secret. Anyway, so polynomials written of degree n can be written in the form right here. Okay, where basically these a's are just our coefficients. And then if you look, we have this n here, and then we have n minus 1, and then it gives us a little section that says, other stuff happens until it counts down to a squared of first power, and then this would be like x to the 0 power. Not 6, 0. And so what's happening with this notation is, like, if this is an nth degree polynomial, like if it was actually the 6th degree, well, there'd be a 6 here where this n is.
Followed by
a 5 and a 4 and a 3. And they might skip
6
some.
minus 1, 6 minus 2.
Right, that's what that notation is saying. And the math notation in here can be tricky, and you really don't need to usually understand it until you get into really high-level math, and all of a sudden you're having to see that stuff all the time.
But look for the pattern on each problem, because that's the key.
The more you see it now, the easier it'll be to understand whenever it's actually important.
Right.
We'll tell you what all of this means. So some definitions here. We talked about monomials last section, that a monomial is one term, polynomial. And so each of these monomials is a term. And so what you do is the leading coefficient and your x, that's a term. And the leading coefficient, remember, always gets whatever sign is in front of it. So if it was like negative 3x to the third, that whole thing is one term, including the negative.
So the terms are broken up by the plus and minus signs.
Right. So they're all broken up. And then there'd be terms in the middle here, broken. Okay? Standard form happens whenever we write it with the degree descending. Like, your biggest degree should be first, followed by the next lowest, followed by the next lowest, and so on.
And if your problem isn't organized that way, for all of the things that we're going to do, you will want to rearrange it.
Yeah.
Making sure that you keep the sign in front of the coefficient with it wherever it travels to.
For example, like 5 minus x squared, hey, that's not in standard form. So when you rewrite that, make sure that negative goes with the x squared. 5 is positive, so rewriting it would look like that.
A good question to ask yourself is, what kind of x squared do we have?
We have a negative one.
We have a negative one, and it's got to stay with it the whole time.
Yes. The constants in front, all of those a's are the coefficients of the polynomial. And we call the first term, if it's in standard form, the leading term. And so it has a leading coefficient, which we talked about the other day.
If you're leading a race, you're in first place.
Yes.
And
I don't know what that feels like personally, but some people would know what that feels like.
I know what that
be
feels
first
like.
In a race.
Yeah, I was first once.
I've been first on a roller coaster, so that's
a leading roller coaster form.
It's similar. Okay. And a naught is a constant term. It's just a number there at the end. You always end with, if there is just a number by itself without an x, that's always the thing that goes last.
Yep.
Okay.
Okay, first example with polynomials, how to deal with a cubic.
How to deal with a cubic?
By graphing.
By graphing. Okay, so we're talking about we're talking about functions with higher degree polynomials, right?
Right.
Okay, so this would be an x cubed graph as its parent function. And so it wants us to describe how to get this graph from an x cubed graph.
X cube's going to have like this kind of a shape.
Yeah.
Or this kind of shape.
So we start with x cubed, and then here's the transformations that are happening. This is from last chapter that we talked about this. We would have this -1 inside.
Super secret opposite society.
Yes, it's inside the parentheses. So it would be right one. I need to remember it mirrors. So
no,
like
it's right one.
No, it's right one.
It's totally to the right
I
one.
watched the video the other one. You need to go right one. That's from their perspective.
Right.
Right one.
Right.
Okay. And then the 2 in front is a vertical stretch.
That's a W.
That's a W.
Then V. Okay, now a W in German makes a V sound, so that would have been okay if you would have left it.
We're not in Germany.
Okay, so we're going to have a vertical stretch by a factor of 2, which means that your y-coordinate, whatever it originally was, will be times 2.
Yes. Why do I keep thinking
Yeah,
3?
so because it's a cubic equation, so
Okay.
you wrote a 3 there.
Okay, I'm sorry. Not really on my game right now. Okay, so we need to sketch this by hand?
By hand, yes. Stretch by hand.
Sketch by hand.
So
Looks like a good start.
that's almost a great looking x and y axis there, Mrs. Stevenson.
Okay, so a normal cubic function, you know, at
Draw,
0.
hey, why don't we draw a normal cubic?
Yeah, let's do that. At 0, we're at 0. At 1, we would be at 1. At -1, we would be at -1. And then after that, it starts going pretty crazy because, like, at 2,
8.
so up
Like
here
I can't
at
even
8,
count that high.
with your shoes
Negative,
on.
yes, with shoes on, I have to actually, if I take my shoes off, I can count right to 8.
So here's a normal cubic function.
Yeah, that's actually really, really good. Much better than I would have been able to do freehand
Well,
style.
thank you.
Yes.
Okay, so we're taking this and we're going to shift it right 1, and we're going to vertically stretch it by 2. So if I take it, I like to do the vertical stretch first because we're multiplying our y values by 2. So at
Right.
0, 0, if we multiply our y value by 2, we're still at 0, 0, 0. Then we move right 1, so that brings us right here.
Okay, I can't argue with that.
Okay, at 1, 1, we multiply our y value by 2, and that gives us 1, 2.
3.
And
2,
then we
2.
move right, so that's right here. And so then at -1, multiply your y value by 2, you get down here at -2, move right 1.
-2.
Now after this, because we were already kind of almost off of our graph with the whole 8 situation, I mean, we know what this is going to look like. It's going to look like a cubic function, and it's going to go up really, really fast.
Really, really quickly, actually.
Yeah, because it's even more quick than the original one was, and the original one was pretty quick.
So now we want to
Support with a grapher.
Support with a grapher, which we will let you do at home on your own. We
Yeah.
will not show you that.
You'll just, right here, just plug this in and see how close you got on your sketch. It should look very similar.
But we can perform a y-intercept.
Oh, right, compute the y-intercept. So to do that, you plug in a 0 where x is.
Because the x-coordinate for the y-axis is 0.
Right. Absolutely. If I plug in 0 for x, I get -1 inside my parentheses. I cube -1, and that gives me -1.
You keep saying it before I can count it out on my fingers.
Why are you counting when you're multiplying?
Because it's, I don't know.
Hey, we actually did go through -2. Like, that was one of our points.
Which means we did the problem right.
It looks good.
Yeah. Hey, now let's graph these bad boys and look at how these polynomials work. And there's really some kind of cool things that make these polynomials up.
Absolutely. And so if we've graphed each of these for you so you can see them as we talk about them.
Put it on your calculator, do it at home.
Yeah, so what's neat is that, you know, if we just have a cubic function, we all know what, like, y equals x cubed looks like, especially since we just did it in the last problem. We all know what x looks like, y equals x, that's a line.
Straight line.
And so, but what's neat is if you think about x cubed plus x, and if you realize what's going on there. Look over here at this graph. We have a cubic function, but here in the middle, where it's really close to 0, this cubic function looks like the line y equals x.
I think I would agree with that.
Which has to do with these being the two monomials that our function is built from. And if it's not obvious on that one, check out the next one. To me, this is where it really brings it home, and it's like, oh, hey, that's actually really neat. X cubed minus x, well, the line y equals -x is going the other direction.
Because of the negative slope.
Because of the negative slope. And check it out. Right here, we have a negative slope right there. And so, yeah, really close to 0, this looks like the line y equals -x, which was this part of this binomial.
So they are completely mashed together, but each part of the monomial takes on specific aspects in the graph. It's really cool.
Yeah, it is really cool. So when you're doing this at home or on your homework, like, that's what we're looking for whenever it says how it's related to the monomials from which it is built. Well, we want you to notice that, hey, here in these two cases, here in the middle, you can see the x or the -x part of it, and then out towards as you go out, that's where the cubic function
Right.
really takes over.
Right. Some things that we can get from this, though, are what are called local extrema. And, you know, there's some debate on exactly 100% what local extrema is, but in this case, it's really evident.
Yes.
Local extrema is going to be a maximum y value or a minimum y value, or like a peak and a valley.
Right.
Is what you're looking
right.
for.
We're looking where the graph switches between increasing and decreasing, or vice versa. So on this first graph, that doesn't happen. This function is increasing the entire time.
The whole time.
And so this would not have any local extrema. So if it tells you to locate it and there aren't any, you need to say, hey, there's no local extrema. And in precalculus, we only care about the local ones, and so if you don't say local, that's fine. A global max or min is a little bit different, and you'll talk
Right.
about that in calculus. The zeros on this graph, well, we could calculate it with our calculator, but this one's really easy to see.
Really, it goes through the zero.
Origin.
The
Zero,
origin.
zero.
One thing, too, with the zero is you could actually see that used several different ways. This particular question asks for a zero. You could also be asked to find a root. You could also be asked to find an x-intercept.
A solution,
You
maybe?
could be asked to find a solution. All of these are the exact same thing. Root, zero, solution, x-intercept, all represent the exact same process.
Is this how we want them to write it? 0 at x equals 0?
That sounds perfect.
That sounds great. So if the 0, if it had intersected somewhere else, you'd just say a 0 at blah, blah, blah.
And
you
when
talk
you're
about
using your
x value.
calculator and you want to find where a graph crosses the x-axis,
You go to second trace.
And guess what?
It's an option.
Zero.
Yeah.
Zero is the option.
You
that you're
find the
looking for.
zeros. And it does kind of like maxes and mins. It asks you for something below. Like it asks you to start over here, and pick a point over here, and then it asks you to guess, and then it guesses in between.
Right.
So the next one we want to look at for the extrema. So we've got an extrema right there, a maximum. I wonder what
Change
that
colors
maximum
on that.
is. Oh,
Get purple, yeah, purple.
yeah, purple.
There you go.
Right here, this is a maximum because this is where the graph switches from increasing to decreasing. We don't have a calculator.
I got a calculator right here. Hold on one second.
And then we also have a minimum over here. We're going to find those two things using our calculator. So you do second trace.
Okay, first,
Max.
yeah, so, yep, so I'm going to go for second trace for x cubed minus x, x cubed minus x. So there it is right there. There's our graph. And on the Inspire, you actually hit the menu Analyze button, and one of the things that you can pick is min or max.
Yep.
And so which one are we on? Max?
Whichever.
So the maximum is going to be, occurs at, there we go, okay. Negative, it's all suspenseful, it's all very suspenseful. 0.577 is your x coordinate,
You said negative, right?
negative 0.577.
Okay.
And the y coordinate is 0.38. And on these kinds of questions, because it builds to AP, the AP coursework, we rounded 3 decimal places, and we would actually encourage you to not round, to just truncate at 3 decimal places so that you don't make a rounding error.
So if I truncate this, that means cut off at 3 decimal places, so that'd actually be 0.384.
0.384.
Okay, so now find the minimum.
So the minimum then is,
Also, I like having the whole point whenever you tell me a max and a min. Don't you like that?
whole points
Whole
are
point.
fabulous. There's no confusion.
Yeah.
So we don't want you to be confused. Hey, guess what?
What?
I think it's going to be very similar.
Oh, you know, it's probably going to be positive 0.577 and negative 0.384. Is that right?
That is 100% correct.
You know how I knew that?
How did you know that?
Because this is an odd function.
Son of a shut the front door.
That didn't even make any sense that you just said that. How
That's
did
crazy.
those things go together?
Well, they just come out.
This is an odd function. Actually, the first one was as well, because for one thing, both of our exponents here are odd. That's one way you can tell. And the other is we've got some symmetry about the origin. You can take what's in the first quadrant, rotate it around, it's in the third quadrant.
One way you could do that is if you take your graph of your calculator and it's got this guy, and if you spin it upside down and it's the exact same graph, that's another way you can tell.
Yeah, yeah. Just turn everything upside down.
Turn everything upside down and it should be the exact same.
We actually have 3 zeros here.
Oh boy, 3 zeros. I know what one of them is.
I think I know what all 3 of them are.
I know one of them is when x equals 0.
Just like last time.
Yes.
I would say the other 2 are at -1 and +1.
I could not argue with that at all.
And, you know, it's pretty easy for us to look at this and, like, it's pretty clear. And also it'd be really easy for us to plug back in and check. But, you know, on your calculator, it's usually not good enough to just guess.
No, don't guess. And don't ever just use trace either on your calculator. Actually use the 0 feature on your calculator.
Yep, second trace.
Second trace on the 84s and menu analyze on the inspires.
Yep.
Okay. Local extrema and zeros of polynomial functions. These are actually super critical things in calculus next year.
Yeah, so it's this theorem that says a polynomial function of degree n has at most n-1 local extrema and at most n zeros.
Right.
So let's think about that. What that says. If we have a polynomial function with degree 3, then at most we have
3 zeros because that's what the degree is.
Yeah, and at most we have two local extrema. And if you think about what the graph of a cubic function, like check out this picture right here. This looks like a cubic function, right? And so look, it goes through 3 times, and that causes it to have a local max and a local min.
Now, just a word of caution, just because you have a cubic function does not necessarily mean you will have 3 distinct places it'll cross the x-axis.
Right. And we'll talk more about that a lot.
Just a super ton.
But at the most, like if you have a cubic function, you should never end up with 4 zeros.
That is correct.
That would be just ridiculously silly.
And you'll always have at least 1.
And yes, for a cubic, yes.
For
if it's odd, you should always have 1.
Right.
If it's even, not so much. For even functions, which what we mean by even is
hey, x to the 4th is an even function
yeah.
because the degree is an even number.
Yeah, like so for those, then it may not go through.
That is correct.
Okay.
That is correct. Okay, so back
now,
to this guy.
Leading term test for polynomial in behavior. You can look at any polynomial function that you want to, any of them, any polynomial, and you can use the leading term test to determine what the in behavior of your graph is. And so the way this works is that all of your functions that have an odd degree, okay, and when we say odd degree, that just means we're talking about the highest power in this case.
The degree.
Okay, the degree of the thing.
Is an odd number.
Okay, if it is an odd number and your coefficient is positive, it looks like a positive cubic function on its in behavior. A positive cubic function goes down and to the left, goes up and to the right. Every single odd and positive function you have will do the same thing.
Has to have that shape.
And then if it's got a negative coefficient, then that flips it across the x-axis, so it would go up to the left and down to the right. You don't have to graph it. You just know that just from looking at the very first term.
And we're not like super concerned with what's going on at the origin in this case either. This is an in behavior deal, so it doesn't matter to us when x is 1 or 2 or 3. What matters to us is when x is like 5 jillion billion.
Yeah, as it goes closer and closer to infinity. So for the even functions, if you have an even degree, then it actually looks like a parabola. They have like, this would be like a
2 arms up,
an x to the 4th kind of thing going on here. But like, just think about a parabola. If you have a positive x squared, then your in behavior is up to the left and up to the right. And the same thing is true for any even degree. If you have a negative coefficient, then they would both point down, go to negative infinity.
One thing that will help a little bit is when you imagine an odd behavior, an odd degree function, and you want to know in behavior, think of Saturday Night Fever and John Travolta as dancing. One arm up, one arm down.
Like disco.
Disco dancing. Yeah. For even behavior, you can always think about a football game, and whenever the home team scores the touchdown, the referee does hands up.
Yep.
In behavior.
Yep.
And what happens if you don't make it on 4th down? You're depressed and hands down. Oh. And so that's one way you could think of in behavior for odd and even degrees.
True. That is one way that you could think of it. So this example, what we're just going to do is we're just going to talk about the end behavior without graphing, because we're going to be that good and be able to do that. For the leading term test, all we do is we look at the term with the highest degree, right? So if they're in standard form, that's the first term.
That's easy if they're in standard form.
Yeah. Okay. So x cubed, what does that tell us the end behavior of the graph is?
Well, the limit as x approaches, what's coming up next?
Should we do negative?
Negative infinity,
Negative
okay.
infinity.
The limit as x approaches negative infinity. In other words, as my x values
Go to
the left, my y values go towards negative infinity.
Okay, because this is a cubic function, so it has to have the end behavior of a cubic function.
It's got to.
Okay, so as you're going to the left, it's going down. As you're going to the right.
So the limit then of f of x as x approaches positive infinity, and again, this is as a limit is equal to what your y value does.
Yes.
So as my x's go really big, my y values approach positive infinity.
Okay, and so this situation is like this very first picture right here, up there. So how about, do you want to go down or to the right?
Let's go. Hey, whatever. Where are we going? Where are we going?
I'm
Where are we going?
red.
All right, red. To the
Oh,
we
that
went.
didn't help. Right.
We went right. We went right. Red is right. They both start with r.
Right.
3x to the fourth. I already know how this is going to go.
Okay, tell me about it.
Well, we've got a fourth degree polynomial here because
do.
that's the largest exponent on a variable, and so that means it has to represent a quadratic equation.
Yeah, it's
at
very
its end
similar.
behavior. At its end behavior. So
Yeah.
the limit as x grows towards negative infinity, my y values approach positive infinity
Because it's
they're
positive.
pointing up.
Positive coefficient here, positive 3.
Also,
Yes.
since the limit is, well, continuing on, before I
Continuing
get
on.
too much more tongue-tied, the limit of f of x as x approaches positive infinity will also be infinity because the y values are growing up.
Yep, both directions.
Yeah,
All
how
right,
about
let's go down to the bottom left now.
Bottom left, so we're going to look at this, it's odd.
Yep.
And
the degree is
The
odd.
degree is odd. And the reason I know,
It's because it's an odd number.
it's an odd number, and the largest number exponent is 3. So the limit as x approaches negative infinity is going to be positive infinity. Why? Because for this particular function, it represents x cubed on its very extreme ends. But not only x cubed, since the leading coefficient is negative, it's x cubed over the x-axis.
Yes.
And so what happens is, as we go to negative infinity, our graph is actually growing up towards positive infinity for the y values.
Right. And as we go towards positive infinity, our y value should be going down towards negative infinity.
I agree. Same thing is going to happen now with x to the fourth. So again, it's just like 3x to the fourth. It's a fourth degree polynomial. It's an even degree polynomial, so we're going to have the shape where both of the sides do the exact same thing.
Right.
At the end
We have
behavior.
that symmetry on the y-axis.
Symmetry on y-axis. And so for this particular guy, as x goes to negative infinity, my graph is actually falling now towards negative infinity for the y values. Why is it falling? Because the negative in the front flips our graph from up above the x-axis to below the x-axis.
Right.
So for both of these then, if one, on an even function, if one end behavior goes to negative infinity, so does the other.
Yep. Okay.
All right, good talk, good talk. Dadgum. All right, so let's graph one of these bad boys and find the
Graph?
zeros. Oh, wait.
No, we can do this algebraic.
Yeah! Algebraic. And can you graph it? Yes, graph it and double check. But guess what? On your AP exam,
Sometimes you don't have that graphing calculator there to tell you what the zeros are.
got to be able to do it by hand.
So on these, if it doesn't specify which way to find the zeros, check and see if you think you can find them yourself without the calculator first.
Always, always.
And then if you can't figure it out, you can try your calculator.
Right.
If on your calculator though, it ends up giving you like nice numbers like 1, 2, 3, -5.
An
Then
integer or
you
something
could
like
have
that.
done it
Yeah.
algebraically. So let's factor.
Let's do. What's in each piece?
There is an x in every single one of these. So let's take
Pull
out
that bad
x.
boy out. Yeah.
That leaves us with x squared plus x minus 6. Okay, so we've factored out an x, and we can factor again now.
Yes, inside the parentheses, it's going to factor to plus 3 minus 2.
Okay, and just, you know, it may have been a while since they've factored, so let's just remind them.
And I hate to bring it up, but factoring, I
It's
know
kind of a big deal.
Yeah, I know you don't like it, but gosh, it's around just a super bunch.
Yeah, it's pretty stinking important. So you figure out what multiplies together to give you -6 that will add to get you a positive 1.
X.
And so you have very limited choices with -6, and so you end up realizing it's 3 and 2. The 3 has to be positive to give us a positive 1. All right, so once we have it all factored out, and so the way you know you have it all factored out is we've got x to the first, x to the first, and x to the first, is to find the zeros, we're actually literally saying, hey, where does this equal 0?
They all equal, yeah.
Where does it equal 0?
That's what we want to know.
And so to figure that out, there's actually 3 answers to this. There's where does this piece equal 0?
Oh, but wait though.
What?
The reason you're doing this is because 0 times anything at all
is 0.
Is 0.
So,
and we've got 3 numbers multiplying together that make a 0.
Right.
So one of them has to be.
One of them has to be. Either it's the x, or the x plus 3, or the x minus 2.
But do we know for sure which one?
We don't. So we have to set them all equal to 0.
Do them all.
These are pretty easy to solve, and so I don't even know that I would expect you to write this step out if you need to. Do it on the notes so that whenever you're looking back, you can tell what you did. But x equals 0, hey, that's definitely a 0. But otherwise, we've got x equals -3 and x equals +2 as our other 2 zeros.
Bingo, bango, bongo.
Finding zeros.
Hey, guess what, kids? You'll never guess. Go ahead, try.
Are you talking to me?
Yeah, kids. You're younger than me. Make sure you're a kid.
Thank you.
Yeah.
What?
We're going to find more zeros.
More zeros.
By hand.
By hand.
Again.
Okay, so we can factor out an x to start off with here. I think that'd be a good way to go, don't you?
I mean, you could probably factor out a square root of 79/8, but it wouldn't help.
Right.
Right.
Okay, so now the thing is, I think we want to remind them how to do this right here, how to factor this.
And there's a couple different ways that you can do it. You get to stick with the way that works best for you. You know, you could always guess and check, which can sometimes be really difficult.
Yep.
So which way are you going to show them?
I'd like to show them slide and divide.
Excellent. Not one of my personal choices, actually.
Really?
But, yeah.
What do you normally pick?
I do that cool square thing. Perhaps we could trade off and show both ways.
Okay, so slide and divide is where you slide what's in front over to the last number so that you end up with x squared minus x. You multiply these. 3 times -2 is -6. That's the slide part. You factor like you normally would. So this actually is very similar to what the last one was, but with a -3 and a +2. And then at the end, you have to do the divide part because it's called slide and divide. You divide both of these numbers by whatever we slid at the beginning. And so if it does reduce, you reduce it. Like, so this is x minus 1. If it doesn't reduce or doesn't reduce completely and you end up with a fraction, you move the bottom of the fraction in front of your x. So this would be 3x plus 2. So that's how you would factor 3x squared minus x using slide and divide.
So, and slide and divide is great. It's not my personal one. So what I would do is
You might not want to write over there because you tend to cut that off whenever you...
I do the box method.
Okay, you're fine. The box method. It's a magical box.
It's a magic box, and...
it looks like, what are those called? The Punnett squares in genetics and biology, where you're splicing genes together to make somebody really tall and have a unibrow.
Yeah, okay. So we're going to take 3x squared and put it here. I have no idea what she was just talking about. Something and we're going to put -2 here. And then we're just going to say, hey, 3x squared times -2, what would that be?
-6x squared.
And it would be -6x squared. So we go, hey, what times what is -6? That adds up to -1. And guess what? It's going to be -3x and +2x. And so now we just factor out on the top row, factor out the greatest common factor on the top and bottom row, and that's going to be a 3x. And on the bottom, it's going to be a 2. So hey, check it out. We match.
Because that's 3x plus 2.
3x plus 2. The other way that we could do it, then to get our other piece, we factor out up and down. And so this guy, the greatest common factor from this is just going to be x. And look, a negative sign and a negative sign make a -1, because that's the biggest number I can get out of both of those. So I end up with the exact same thing.
Yes. Either way you want to do it.
Either way you
fine.
want to do it. And if one of those ways is confusing to you, by all means,
don't
do it.
Yeah. So now we've successfully figured out what it is when we factor it. We have x in front still, and then we need x minus 1, 3x plus 2. We need to find the zeros, which means we still have to set these equal to 0 and solve. Well, the first one's easy. We have x equals 0. The second one's easy. X minus 1 equals 0 means x equals +1.
Easy peasy lemon squeezy.
Yes. And then 3x plus 2 equals 0. We'd have to subtract the 2 over and divide by 3. And if you can do that in your head, that's fine. That's a reasonable thing to be able to do in your head. So x equals -2/3 on that last one.
And there's all your zeros, and that's, you know, it took us a little while longer, but we factored twice.
Yeah, we showed you 2 ways. So whichever way you choose, do it that way.
Multiplicity.
Multiplicity is a fun thing.
And confusing potentially at times.
It could be. So multiplicity is talking about that whenever we factor, like in the last couple examples, and we're getting a 0, you know, sometimes you can factor and end up with the same factor more than once.
That'd be multiples of the same factor.
It'd be multiples of the same factor. Like we could, if we had factored something, we could have ended up with something like x minus 3 times x minus 3 times x minus 3, which, by the way, we could have written as x minus 3 cubed, right?
3 of them puppies.
Okay, but the whole point of this is if I set each part of this equal to 0, I get the answer of x equals +3.
Every time.
And so that's 3 times, right?
Yeah, but
And
it
that's
only
what's-
crosses it once at
That's
3.
what we call a multiplicity of 3. And so whenever you factor and you end up with an answer more than once, however many times you end up with it, that's the multiplicity. If what you get is an odd number, an odd multiplicity means the graph crosses the x-axis at that 0. An even multiplicity means the graph touches the x-axis at that point, but then it bounces back up or bounces down. It doesn't actually go through at that point.
I think a better definition to work with is the bounce part. I think the touch can be.
Okay, so
I think bounce is a great way to describe that.
Bounces off.
It bounces off, and it bounces in the direction that it bounces on the side of the x-axis you were already on.
Yeah.
So if you were up and it bounces
bounces back
up.
up. So let's look at an example of this. We're going to state the degree and list the zeros of this function, state the multiplicity, and whether or not the graph crosses or touches the x-axis at the x-intercept. Sketch the graph by hand.
Easy for Mrs. Stevenson to read.
Yes. Okay, so the degree of this right here, f of x equals, they've already factored it for us, which, hey, that's good because this would have been tough to factor ourselves.
Yeah, yikes.
Okay, so our degree is we've got a cubed, which if we multiplied this out would give us an x cubed.
X cubed.
And then if we multiplied that with this, which is going to give us a highest degree of x squared, and we put those together.
And multiply them like it's saying to do.
X to the third times x to the second is x to the fifth.
Add exponents when multiplied.
Okay, so this is a 5th degree polynomial. All right, list the zeros of the function. Well,
Easy peasy.
this first part, x plus 1 equals 0, means I have a 0 at -1. The second part
X minus 2.
means I have 1 at x equals +2.
You might notice the super secret opposite society is out in strength today.
Right, right. If I set x plus 1 equal to 0, I always have to change the sign whenever I move it over. So if you remember, hey, parentheses means do the opposite, you're good to go. Now, the multiplicity is whatever this exponent is. The 0 of x equals -1 has a multiplicity of 3 because it happens 3 times. So if it's a multiplicity of 3, that means that it crosses
The
at this 0.
x-axis one time when the x-coordinate is -1.
Yeah. For the second 0, x equals 2, then we have an even multiplicity. We have a multiplicity of 2, which means that it touches or bounces. Or not crosses. What?
That's,
Touches, bounces.
Touch, bounce,
Touches
no
is
cross.
a little bit more mathematical, actually, I guess. Like, books use the word touch.
Okay.
So, I mean, it's whatever, though. Let's sketch. Yeah, let's not do the whole you're not touching me fiasco again.
That's a limit.
Yes. Okay, so we need to graph this, and this is a sketch using what we know. Okay, so let me make some tick marks.
One thing we know is that it's odd, which means that in behavior is going to match that of x cubed.
Yeah, it's a 5th degree polynomial, so it looks to me like also it would be a positive leading coefficient.
I believe it also would be a positive coefficient.
Since there's nothing in front of our x's, we'd basically end up with an x to the 5th.
Without
if we
anything
multiplied
in front
it all
of it.
out.
That is correct.
So we know that at the end of our function, we should be
pointing down on the left and up on the right when it's all said and done.
Now to figure out the squiggles in the middle, we go over here to our zeros. We know it crosses at -1.
Right.
And we know that it touches at 2.
Right.
Okay, so if I cross the x-axis here, and I know that I'm going down and to the left.
I think that is a totally appropriate left-hand side for this graph.
We could go ahead, just to be a little picky, we could go ahead and find the y-intercept real quick by putting zeros here. We'd get 1 cubed times -2 squared.
4. I didn't even have to take my shoes off to count that one.
That's great. You're really improving. So we would go all the way up here, like this crosses at 4, and then it has to come back down at some point so that we can touch and then start going back up. See how it touched but didn't go through on that point?
Bounced it right off the old x-axis there, and we don't know where the maximum occurs 100%. Like, we can make a good educated guess, but that's not what we're really interested in right now with this particular problem.
Yeah. So that's a rough sketch. Now if you graph it by hand, because we might as well graph it by hand and see how close we are, then that's a great way to check yourself. If it
graph it by calculator.
Yeah. If it says sketch by hand, by all means check it with your calculator.
Yes.
But there you go. That's a rough sketch. Hello there.
Hello indeed. So finding zeros.
I'm going to really keep going
Yeah, sure,
after
might as
that
well.
start. Okay.
Finding zeros, but now doing it on a calculator because Mrs. Stevenson over here, Fancy Pants Stevenson, could probably factor this guy. I can't.
I honestly can't. I'm going to tell you straight up. Well, I don't want to, is really the more important thing. What we would do is we'd stick this into the calculator. The way you know that this is probably a calculator situation, for one thing, the decimals are a pretty good indication. Normally with decimals and fractions, factoring is not a very good idea. And then if we graph it, we graph this on Desmos, the online graphing calculator, who are not paying me to say that. And this is what we came up with. Well, for one thing, if you don't understand how to find the zeros on your calculator, we're going to give you a link that just shows you that. But it's pretty easy to do, especially since we've done max and min. So we're not going to stick it in right here to distract you. But what we can see is clearly, oh, maybe we could have factored this, because clearly there's a 0 at 2.
Right there too, yeah.
I mean, that's pretty clear that there is a 0 at 2. What is up with my pen thickness? Why did the pen go all crazy?
I don't know.
Okay, x equals 2, and then clearly something is happening here that we just can't see well enough from this graph. So remember the trick of the box.
Yeah, the box is going to be really handy here, or even just zoom in, but on the origin, because that's where it looks like something's happening.
Yeah,
so
since
I'm doing
it is
that,
on the origin,
I'm doing that right
might work out well. I personally like zoom box better. I feel like I've been jaded by zoom in and zoom out too many times to trust them.
It's entirely possible.
There's a point where you say, fool me once, shame on you, fool me twice, shame on me.
That is correct. What you have just stated is a correct thing.
Are you finding that?
I'm zaboxing right now.
And when you zoom into that box, like this part in the middle that it looks constant, you got to understand, it has to be a super strange looking function to ever end up with a constant. Like, it is going down. Mm-hmm. Okay, that whole time. Like, it evens off a little bit, but we wouldn't actually call that constant, right?
No, it is not constant, although it might be falling at a very, very small
very,
rate.
very small, minuscule amount of falling. Like, we're talking constants, what? We get constants with absolute value functions, and that's it, right?
Right.
And that's only if they're really, really weird. So, are you going to find that 0?
I'm working on it.
Find the 0?
Yep.
Are you going to find the 0?
Yep. my calculator is in super slow mode right now, and it looks like that 0 is at negative 0.1.
So x equals negative 0.1?
Yeah.
Is that the only decimal?
That's what it shows.
Why? Oh, okay. And that's the only two places where we go through. Now, I mean, that's all there's to it.
That's all there is to it. Now, also, keep in mind that how many zeros could we have on this particular problem?
We could have had as many as 4.
But we only had 2, so you will always get zeros in, for these kinds of problems in pairs, I think is safe to say, for even polynomials.
I think that's true. For even polynomials, you'd always get them in pairs.
Mm-hmm. Hey there, hi there, ho there, again.
Hi, it's time for example 8. Using only algebra, find a cubic function with the given zeros, support by graphing your answer.
Which we'll not do.
So we're not going to support it by graphing our answer?
They can graph it at home.
You can graph it at home. Okay.
Yeah.
Okay. So they're saying that these are our zeros, right? That
roots? Could they be roots?
They could be roots. They could be zeros. They could be solutions.
All right.
Those all mean the same thing. X-intercepts. X equals these 3 things. And we want to find a cubic function that would give us those as answers. It's really pretty easy to do. If it's a function, we've got like an f of x situation going on. And you know how whenever we find them, we set each part equal to 0? Well, we're going to do the opposite of that, and we're going to stick these in parentheses. When we do, we change the signs.
Super secret opposite society.
Exactly. Because once I have this written out, like, don't you see if we set this equal to 0, we can solve for that and get 1, solve for that and get 1. Why am I pointing at the screen? Solve for this and get 1, solve for this and get 3, solve for this and get negative 2.
So when you solve each one out, though, you do get 1, 3, and negative 2, and that's the important part.
That is the important part. Now, we're trying to multiply this out so that we get a real life polynomial. Okay.
Real life function.
So let's multiply.
Let's do.
Okay, so we're going to start by foiling 2 of them. So first, can we handle outer and inner at the same time?
Yeah, outer, inner together. Ready, negative 4, go.
Okay, so negative 3x plus negative 1x, which is negative 4x. And then last, negative 1 times negative 3 is plus 3. That's the first 2 parentheses multiplied together, then we got to multiply another parentheses together. So this is where you distribute twice.
You're going to probably have to have a little work on this one, because even for us as mathematicians and people that do this all the time.
I wouldn't sit here and try to do this in my head.
Yeah, doing this in your head is no deal.
Unacceptable, actually.
Right.
Prove how awesome your math skills are by writing all of the steps down. I'm going to do this cool thing where now
stack it, yes.
Yeah, stack it. So now when I distribute the 2 through, I'm lining up my x squareds, my x's, and these other things. And so now you can see that our like terms are coming down in columns.
God, that's genius.
Yep. I actually sometimes forget that this is such a great way to do it, but then I saw a student doing it the other day. I don't remember who, but you may know who you are, and I think you're awesome.
Yeah, that really
Shout out
does.
to random student that I don't remember who was doing it.
Random students.
Okay, that's the first one. There would be like an f of x out here.
Yeah, or perhaps a y equals,
or
maybe?
y equals. That would make it a function. Really, by itself, it's not one. But
No.
f of x equals or y equals. All right, so that's our first example, and then here's where it gets fun.
Yeah, this here is where life. This is real life.
Which
For
is
real.
Okay, yeah. I was about to say which is funny because we have imaginary numbers, but those aren't imaginary. They're just irrational.
Yeah, they're being irrational. They're your parents yelling at you after you show up 2 minutes after curfew. Being irrational.
Whose side are you on?
What I meant to say was, what you want to do is, it actually will help on this if you write down exactly what's going on. So Mrs. Stevenson has already started, and with the radicals in there, you need to write it out. So x minus, and then put your parenthesis in there, and what your number is, 2 plus the square root of 3. Okay, and then close everything off and do another one, x minus, and then put your parenthesis in there, and then 2 minus radical 3. So this is your starter, and it looks brutal, okay?
But it's not so bad.
It's not so bad.
It's misunderstood. It's irrational.
It is. But here's what you do. Start with the radical part first. I'm just telling you right now, if you don't do the radical part first, yeah, we're going to distribute in just a second. But if you don't start with the radical part first, your life will just become miserable. So
Oh, you mean like this part?
Yeah, start with that whole part
Okay.
first. Okay, so go ahead and distribute the negative sign in there and on both of those. So you'll end up with x minus 2 minus radical 3
Right.
and x minus 2 plus radical 3.
Right.
And here's the trick that you know if you go in the right direction. When you do your math here,
Square roots should go away.
the square roots should totally be
They
gone.
should not stay in there.
Right. So
Which is a good thing.
yes, we don't want them. So again, starting it back. Well, x times x, that's easy. That's just x squared.
Yes.
Okay.
We're pretending, okay, here's what we're really doing, so in case we lose you. We're pretending that this is a number and that this is a number, and we are foiling,
Yeah.
okay?
Big
That's what's
chunkage
about to
foil.
happen. So, to do that, we have to, go ahead.
So to do that, what we're going to do is we're just going to follow our rules of first, outer, inner, last parts. Well, the last part, okay, at the very end is going to be, just write it out, -2 minus square root of 3 and a -2 plus square root of 3. We're actually doing this part.
This is our last term.
This
from
is our
FOIL.
last term. So it will actually be 4 minus 3. There's no middle term on this guy. And that's what we love about it. 4 minus 3.
Because when you do first, outer, inner, last, the outer and inner terms on this will cancel each other out.
Mm-hmm.
Your first is -2 times -2, which is 4. And then a negative, this tends to trip people up. So a negative square root of 3 times the square root of 3 is negative square root of 9, which is -3.
Right.
So that's how we got this -3 here.
Right.
So 4 minus 3 equals 1. So our last term here for foiling out this part is going to be a +1.
Plus 1.
So we need to figure out what's in the middle. And so when you do foil and you do outer and inner, you always end up adding those together because they're always like terms.
Right.
So, and there's always an x with it.
Right.
So we need to add together these two numbers so that we can get those outer and inner terms added together.
Right.
So what we're doing is -2 minus square root of 3 plus -2 plus root 3. Okay, and so our square roots go away. -2 plus -2 is -4.
And then x.
And then we put an x with it. So that's that all worked out. And so the key thing is that you multiply them together.
Yes.
And that you add them together.
Yes.
And that tells you those two numbers that go in there. And if you end up with radicals in there, you screwed up.
You've got a mistake. And we showed you, this is like a little trick that we just showed you. So this is going to be a little uncomfortable to watch the first time. You may need to watch this particular part a couple times to see what we're doing. But I'm telling you, once you have this trick figured out, life is
grand.
Oh, super grand. It's
Yeah.
it's like
a holiday.
chocolate and peanut butter.
So let's finish distributing.
Yeah, let's do. So
Okay.
now we're just going to wrap this problem up by distributing through again. And if you go ahead and stack these guys like we did in green just a minute ago, everything lines up just 100% perfectamente. Also notice that there's no radicals at all left in our problem. They're gone. They left after step number 1. So if there's a radical left in there somewhere, you've got a little whoops that needs to be.
A little bit of a whoopsie
Yeah,
daisy.
just go check your math and make sure. So there you go.
And then put that f of x right there.
Or y.
Or y. And that's it right there.
Bingo, bango, bongo.
Yep.
Yep.
Yep, yep.
Yep, yep.
Yep, yep, yep.
Okay, intermediate value theorem. This is a biggie. This is a really, really important theorem, and this is baby step number 1 of this theorem. There's all kinds of kind of intermediate value theorem corollaries. A lot of them you're going to talk about next year.
Yeah, but we're going to talk about this part of the intermediate value theorem, this part right here. So it says if a and b are real numbers with a is less than b, so that means a is a smaller number than b.
Right.
And if f is continuous on the interval from a to b.
In other words, when you put your pencil down and you start to draw this graph, you never pick your pencil up from a to b.
Right. Then f takes on every value between f of a and f of b. Okay, f of a is the y value at a, f of b is the y value of b. So, in other words, if y naught is between f of a and f of b, then y naught equals f of c for some number c in a to b. So that's the part where I think it gets confusing.
It's really fancy stuff in there, but basically what we're saying is if you take one x value to start and one x value to stop, that you will get a unique y value for every x value in between.
Right, because it's continuous.
Because it's a continuous
function. And so what that is really important, what's really important about that is this next part. If f of a and f of b have opposite signs, so if like in this graph,
one y coordinate is negative,
and the next one is positive, then at some point between a and b, you have to have a 0.
you have to. It has to cross the x-axis and give us a 0 root or solution. It has to do that.
So here's what that lets us do, kind of. Let's give. I'm gonna try this and see if you follow what I'm saying. Like, okay, what if we know it's a continuous function, and they tell us we've got like 2, -5, and 7.
3.
I was actually going to go with 3, and then I switched to 6. How
Okay.
weird is that?
Yeah,
okay?
it's really weird.
Okay, so let's say that they tell us we've got some random function. It's continuous between 2 and 7, and these 2 points go through it. We know because this is a negative and because this is a positive, we know somewhere between there is a 0.
It crosses the x-axis.
It crosses the x-axis.
So,
It
do we
has
know?
to.
Do we know exactly where?
We don't know exactly where.
We don't know.
But let's think about. Let's just graph it really quick. 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So 2, -5 is down here. 7, 6 is up here. So doesn't that make sense that if this is a continuous curve between these points, it doesn't matter what it looks like. It could be all sorts of squiggly.
It could bounce 5 times in
Yeah,
there.
and it could even go through more than once, right?
Sure.
But we're guaranteed it has to have at least one 0.
one.
And it could be like a straight line. Oh, look. Well, that's
Hey,
not
look at
really a
that.
straight line, but a kind of straight line. You know, that went through once. Or it could go up and down.
Who knows?
But we know it goes through at least once. Because
Intermediate value theorem.
The intermediate value theorem, also known as IVT. I don't
Yeah.
know, is it known as that?
It is now.
It is now, IVT.
Yeah, the IVT. Wow, that was a really long session of notes.
Yeah, that was pretty tough.
Pretty tough. So,
But it's going to be worth it
it's
because
gonna-
we learned a lot.
yes, we did. And right now, we are showing you the super secret code word.
Well, not right now.
Not
Hang on,
right now.
Let me
Hold
hear
on.
to that. Okay.
Right now, this is the super secret code word. And if you
Code
made
phrase.
it code phrase, if you made it all the way to the end, and you see this code phrase right now, make sure and let Mrs. Stevenson and I know. But don't tell anybody else. Let
Yeah,
your friends discover on their own.
Yeah, don't tell anybody else that this is here. We want to see who really watched the video.
It'll be worth your while.
Yeah.
I promise.
Yeah, it'll be great.
Yeah, it'll be great. Have a good day.
You too. I mean.